Behind every artificial intelligence cluster, smartphone, and modern fighter jet lies a microscopic piece of silicon that costs $20 billion to manufacture. Turning raw sand into cutting-edge 2-nanometer microchips requires the most expensive, complex real estate assets on Earth. Building a single semiconductor fabrication plant, or fab, demands an astronomical capital expenditure ranging between $15 billion and $20 billion. A massive portion of this upfront capex goes directly into purchasing extreme ultraviolet lithography machines built exclusively by ASML. A single EUV scanner costs over $200 million and requires 3 Boeing 747 cargo planes just to transport its delicate components. Inside the machine, high-powered lasers blast 50,000 drops of molten tin every second to generate extreme ultraviolet light capable of etching atomic-scale circuits onto silicon wafers. To house these delicate machines, fab owners must construct clean rooms that are 10,000 times cleaner than a hospital operating room. The entire facility is built on massive concrete stilts driven deep into bedrock to eliminate micro-vibrations from nearby highway traffic. Even a minor ground vibration can misalign the lithography lasers, instantly ruining hundreds of millions of dollars in delicate microscopic manufacturing. Because technology degrades rapidly, a fab's high-tech machinery depreciates over 50% of its value in just 3 to 5 years. In the global semiconductor ecosystem, there's a sharp financial divide between companies that design chips and companies that physically manufacture them. Fabless design giants like NVIDIA, Apple, and AMD create the microscopic blueprints, while pure-play foundries like TSMC execute the physical manufacturing. Foundries charge fabless clients per silicon wafer processed, with advanced 3-nanometer wafers commanding prices upwards of $20,000 each. However, a foundry's profitability is governed entirely by a single metric: manufacturing yield rate. Yield represents the percentage of functional, working chips harvested from a single silicon wafer versus defective chips that must be discarded. When a new manufacturing process node launches, initial yields can be as low as 30%, causing the foundry to lose cash on every batch. Engineers work around the clock tweaking chemical recipes and gas filtration to push yield rates above 90%. Once yield rates cross the 90% threshold, the fab turns into an absolute cash-printing machine. Because upfront capex is fixed, every additional percentage point of yield translates directly into pure net profit margin. Once operational, running a semiconductor fab involves eye-watering daily operational expenses. A large-scale fab consumes over 1 million gallons of water every single day to wash silicon wafers between chemical etching steps. This is not ordinary tap water. It must be purified into ultra-pure water, stripped of every single ion, mineral, and microscopic particle. Filtering and recycling millions of gallons of ultra-pure water requires massive industrial filtration plants on site, driving up daily utility OpEx. In addition, fabs require a massive, uninterrupted power supply equivalent to the energy consumption of a small city. A single power outage lasting just half a second can shut down cleanroom pumps, disrupt vacuum chambers, and destroy hundreds of millions of dollars in active inventory. To mitigate grid risk, fab owners install dedicated electrical substations and massive diesel generator backups capable of instant failover. Unlike traditional industrial infrastructure that lasts 40 years, semiconductor fabs live on a relentless treadmill of technological obsolescence. Chip architectures follow Moore's law, meaning a state-of-the-art fab loses its competitive edge within 4 to 6 years as smaller nanometer nodes emerge. This forces foundry owners to reinvest up to 30% of annual revenue back into research and development and new equipment upgrades. To de-risk these continuous multi-billion-dollar upgrades, foundries require clients to pay upfront NRE fees, known as non-recurring engineering costs. Designing a new chip architecture and creating the physical photomask sets, a process known as tape-out, costs upwards of $500 million. By forcing chip designers to co-invest during the tape-out phase, foundries lock in guaranteed wafer production volumes years before the chips hit the market. Beyond private capital and physics, semiconductor foundries represent the ultimate geographic choke points of the global economy. Over 90% of the world's most advanced processors are manufactured on a single island in East Asia. This dangerous concentration of critical supply chains has triggered a global race for sovereign semiconductor independence. Governments worldwide are handing out tens of billions of dollars in direct CHIPS Act subsidies and tax credits to incentivize domestic fab construction. However, Building fabs in Western nations faces immense cost headwinds, where construction labor, environmental permitting, and engineering payroll can be 40% higher. Despite these elevated operational costs, national security mandates mean that sovereign-backed chip fabs will remain the highest capital, highest retention asset class on Earth.